Okay, so in this video, I'm going to take a quick look at a few things that came up from the magnetization quiz I got you to do. So the first thing I want to address is that soft magnetic materials are always attracted to permanent magnets, because this is something that people were saying that if you approach with a south pole, it'll attract, and if you approach with a north pole, it'll repel. And that's something else entirely. So soft magnetic materials like iron are always attracted to permanent magnets. So the reason why is because when you approach with a different pole, the domains will align themselves in a different direction. So you can see down here on this first one, where we're approaching with a south pole, the domains align themselves. So the little domain indicates where the north and the south pole of this little magnet are. So you can see that the north end ends up at this end because it's attracted to the south pole, and you get attraction here. Whereas when the north pole approaches, the domain aligns itself in the opposite direction and it's still attracted. So soft magnetic materials always attracted to permanent magnets. The next thing that cropped up was to do with magnetization. So I got quite a few people writing that you will pass a DC current through the material and that will turn it into a magnet. And that's just not correct. To my knowledge anyway, if you pass a current through a magnet, nothing is going to happen. Okay, unless you make it sufficiently hot, and that will actually demagnetize it potentially. So the key idea is you need a separate magnet. So the battery and the wire themselves form an electromagnet because you've got moving charged particles which create a magnetic field. And then by putting your material inside that electromagnet, it too gets magnetized and becomes a magnet. So you place it inside a coil carrying a direct current. You don't pass the direct current through the material. So the final part I want to look at is demagnetization. So most people are fine with heating and hammering it. So it's this part where we slowly remove the object from a coil carrying an alternating current. So I want to flesh that out a little bit more and give you a bit more detail to explain why we need the slowly removing and why it needs to be an alternating current. So first part, why does it have to be AC? The reason for this is we need a electromagnet in which the field is constantly flipping direction. So you can see in this diagram over here on the left, we had a current going in here and out here, whereas it's the opposite on this one on the right. So this one, the current is going in on the right and out on the left. This is exactly what would happen if you put an AC current through this coil. Sometimes the current would go in the left, sometimes it would be going in the right, and that will be changing. And if you're in the UK and you plug it into a main supply, it will be changing 50 times a second. Okay, so this is happening very quickly. So the reason we need AC is we need an electromagnet where the poles are constantly flipping. So on the left, the north pole is on the left, south pole is on the right, and that's exactly the opposite. I've actually got those the wrong way around. That's actually a south pole. That's actually a north pole. That's actually a north pole. That's a south pole. Because this end on the left, you can see the current is going around clockwise, so that's actually a south pole. So essentially, that's what we need. We need the poles constantly flipping around. That's why it needs to be AC. As to why we need that and why it needs to be moving, that's what we can sort of move on to have a look at. So why can't it be stationary, which is what quite a few people wrote. So if we put a magnetic in this field, let's say we did it on the one on the left, what would happen is all its domains would align with the arrows. So you can see the domains would all line up to the left like this. If we put the same magnetic field in magnet in the one on the right, they'd all line up in the opposite direction. But the key is they're all lined up in the same direction if we have it sitting in the field. So it doesn't matter that the field is flip-flopping, the domains all are lined up in the same direction. So with our magnet that we put into the coil, would its poles be flipping? Yeah, probably. But would it still be a magnet? Yes, it would. So it can't be stationary. Okay, so why does it have to be slow? Well, if you move it really quickly out the field, you just don't give the domains time to realign. So that's why it has to be slow. So what happens when you have the material moving? Well, essentially the key idea is that as each part of the material exits the field, it will no longer be realigned by the field. And because the field is alternating, this is going to mean that as each part exits, it's going to be aligned in different directions. So let's say this part here on the left-hand side exits first. So it exits in this alignment here. Now, a fraction of a second later, when this next part exits, it's aligned in the opposite direction. So you can see that in this one here. So this part is now aligned in this direction because the electromagnetic field flip-flopped. Then this part of it leaves the field, and that's aligned in this direction. And then finally, this part leaves the field, and now the field has changed again, so it's aligned in this direction. Now, this is an overly simplified model. They're not going to end up in sort of like right, left, like this. But the key idea is that these fields will all cancel each other out because they're all opposite to each other. So they'll cancel each other out, and this part on the right-hand side won't have a magnetic field, so it's been demagnetized. Now, like I said, it has been overly simplified like that. So when you apply a magnetic field, not all the domains align at the same time. It takes a while for them all to line up. So there are some oversimplifications here, but it gives you the right idea that as each part leaves the magnetic field, the domains are aligned in different directions and they all cancel each other out. That's the key idea here. But this is all looking at the process of demagnetization and the fact that we need to slowly remove it from a coil carrying alternating current. And it's not that we pass the alternating current through the magnet, it's through the coil.